Picture this for a second. Imagine a substance out there that's so perfectly stable and honestly, so relentlessly infectious that just a single microscopic droplet of the stuff could hypothetically unravel the entire universe, like literally converting everything it touches into more of itself. Welcome to This Explainer. Today, we're unpacking a concept that sounds exactly like a sci-fi apocalypse, but it's actually deeply rooted in the real cutting-edge world of quantum physics. We're talking about strange matter. And exploring this topic immediately begs a massive, universe-altering question. Could an entirely different form of matter be hiding right now inside the densest objects in the cosmos? Because if the physics theories we're about to unpack are on the money, this exotic substance might not just be lurking out there in the dark. It could actually be the true, absolute underlying nature of physical reality itself. Okay, let's dive into this. Here's our roadmap for today. First, the cosmic mystery. Second, quarks and strange matter. Third, the strange matter hypothesis. Fourth, neutron stars and strangelets. And finally, the search for evidence. Part 1. The cosmic mystery, a theoretical contagion. Moving to Part 2. Quarks and strange matter, the quantum ingredients. So everything you know, your body, the screen you're looking at, the Earth itself, the stars, that's all ordinary matter. It's built from atomic nuclei, which are in turn made of just two fundamental types of particles, up quarks and down quarks. That's the standard recipe for our reality. But strange matter introduces a total wild card. It's a hypothetical form of matter made up of roughly equal proportions of up, down, and a third type, the strange quark, all existing together in this perfect chemical equilibrium. Now, what's really interesting about what you're seeing charted out here is the dramatic difference between the two. Look down at the bottom edge for a sec. Point A represents ordinary atomic nuclei. It's comprised entirely of up and down quarks with zero strange quarks. But if you look right at the very center of the triangle, at point S, that is strange matter. It sits perfectly balanced right in the middle, like a precise three-part cocktail of up, down, and strange quarks. So, what exactly is this third ingredient doing? Well, a strange quark is the third lightest quark flavor in quantum chromodynamics. It carries a negative charge, and it's significantly heavier than the up or down quarks. Now, you'd logically think that adding a heavier, clunkier particle to the mix would make the matter more unstable, right? But under extreme density, it does the exact opposite. Because of a quantum rule called the Pauli exclusion principle, you simply cannot cram too many identical quarks into the same energy state. It's kind of like trying to shove way too many people into a tiny elevator. You get this massive outward pressure. But by introducing a new flavor, the strange quark, it effectively relieves all that subatomic overcrowding. It opens up a whole new set of energy levels, which actually lowers the overall average energy of the system. Bottom line, it makes it incredibly stable. Which brings us to Part 3, the strange matter hypothesis, the absolute ground state. Back in 1984, physicist Edward Witten built on some earlier theories by A.R. Bodmer, and he proposed something completely radical. What if strange matter is actually the true absolute ground state of the universe? If that's true, then ordinary matter, even something as solid as iron, is just metastable. It's basically an illusion of stability that just hasn't decayed yet. And this brilliantly illustrates the terrifying consequence of that hypothesis. What happens during contact? If a negatively charged fragment of strange matter, which we call a strangelet, contacts normal matter, it wouldn't just bounce off. It would absorb the normal nuclei, dissolve their protons and neutrons down into a free quark bath, convert some of them to strange quarks, and then release a massive amount of energy. The strangelet grows, effectively acting like this unstoppable subatomic contagion that converts absolutely everything in its path. Okay, Part 4. Neutron stars incubating strangelets. The only places in the modern universe with enough sheer pressure to actually force quarks into this strange state are the cores of neutron stars. These are the ultra-dense, burnt-out corpses of exploded supernova. Some of these compact stars have been observed spinning up to 716 times a second. The pressure inside is so immense, so impossible, that it triggers a quantum process called deconfinement. The literal physical boundaries of protons and neutrons are crushed out of existence, dissolving into a fluid of free quarks. If the pressure converts enough of them into strange quarks, the whole stellar core could transition. Boom, you've birthed a strange quark star. And as we all know, the universe is a famously violent place. When two of these incredibly dense, strange stars collide and merge, they release an explosive amount of energy, potentially up to 10 to the 53rd ergs, which powers massive gamma ray bursts. But crucially, these violent collisions could eject tiny, highly dense fragments of strange matter straight out into the interstellar medium. These fragments are the strangelets. They can be incredibly small, like the size of a single atomic nucleus, or they could stretch for kilometers. The smaller strangelets carry a uniquely low positive charge, meaning they'd have very little electromagnetic interaction with normal matter, so they would just quietly, stealthily drift through the cosmos. Finally, Part 5, the search for evidence. Hunting cosmic contagions. We have actually been trying to solve this mystery for decades. Tracing the historical arc, we first discovered the existence of strange quarks way back in 1947 through early cosmic ray observations. By 1971, Bodmer was already theorizing about collapsed quark nuclei. In 1984, Edward Witten formally pushed the strange matter hypothesis into the spotlight. Fast forward to 2011, and we literally took the hunt to orbit with the installation of the Alpha Magnetic Spectrometer on the International Space Station. So the crucial point here is how modern science is attacking this from every conceivable angle to see if it's real. We're smashing atoms together at nearly the speed of light in heavy ion colliders like the LHC and Reich to briefly recreate the quark-gluon plasma of the early universe. We're using gravitational wave observatories like LIGO to listen to the ripples of merging neutron stars, checking if their mass and radius profiles align better with strange stars. We are even looking for the tracks of ancient strangelets embedded in lunar samples and meteorites. But one of our absolute best tools is the AMS-02. Operating in the harsh environment of space for over a decade, it has collected a staggering 230 trillion cosmic ray events. That is an insane amount of data. It's essentially out there sifting through the high-speed debris of the universe, hunting for one incredibly specific anomaly, particles with massive weight but a tiny electric charge. That's the fingerprint of a strangelet. And what's really fascinating is that the extremely precise data coming from AMS-02 is already conflicting with our standard models of cosmic rays. It's heavily hinting that there's an entirely new, unexplained layer of physics just waiting for us in the dark. Which leaves us with this final, staggering thought. If the strange matter hypothesis proves correct, and this perfectly balanced three-quark exotic material is in fact the true, absolute ground state of the entire universe, are the very atoms we are made of just a temporary, metastable illusion? Could everything we know eventually succumb to the ultimate cosmic contagion? It completely reframes humanity's fragile, fleeting place in the cosmos. Let that sink in. Thank you so much for exploring this mind-bending topic with me in this explainer, and keep your curiosity burning.